Welcome to all. Now I'm going to start the numerical problems on 1D bar element. So as I told, for boundary conditions we are going to use two approach, elimination approach and penalty approach. Now we are going to uh, solve the problems using a elimination approach. So here there are different cases will comes. So like mom, how you done the problems on bar, same thing like uniform bar will be there, stepped bar will be there, then taper bar, same thing here. First case we are taking uniform bar with an axial load condition. So the problem is the bar shown in figure subjected to axial loading, find nodal displacement, stress in each element and reaction at support. So this is the bar they given and it's having a subject to a axial load of 10 kilonewton. Corresponding Young's modulus is 200 GPa and area is 10 to the power of 4 millimeter to the power of 4 and the length of the bar is 1000. So the cross section of the bar is same everywhere, that's why it's called uniform bar. So this is a problem they given. We need to find what is the nodal displacement. Nodal displacement nothing but the displacement at each node and stress on each element and also reaction. So as you know, for all numerical problem, the first step is to write the given data, and also corresponding all the units are converted into a common units. So here area given E is 210 into GPa gigapascal. So everywhere mm, either you can keep it in mm or a meter or centimeter. Usually will follow mm only. 210 GPa, therefore conversion of 210 GPa is 1 GPa is 1 into 10 raised to 3 Newton per mm square. Therefore 210 into 10 raised to 3 Newton per mm square, or also we can call it as, we can write it this one as 2 to 10 raised to 5 Newton per mm square. So and also length is 100 mm and load is 1000 Newton. So as we discussed in the previous videos, the steps involved, there are totally 8 to 9 steps is there. The first step we need to write the finite element model. So now that means the discretization process we need to do. So you can divide as you wish, but let us divide only one element. Therefore corresponding nodes are become only 1 and 2. For each element the nodes are 2. So here the corresponding nodal displacement is Q1 and Q2, and node 1 the force acting is F1 and F2 and the length is L. Where Q1 Q2 are the nodal displacement, F1 F2 are the nodal forces. So that is step number 1. We need to write it as an element model. And step number 2 is we have to find the element stiffness matrix. Here there is one element, therefore we have to find one element stiffness matrix. The two element means 2. It's only K1. K1 is A1 E1 by L1, 1 minus 1 minus 1 1. Where E1 L1 you substitute the values, then you simplify it. See now. So one more thing very important is, so here after simplifying we written as 10 power 6 2 minus 2 minus 2 into 2. That means here the 10 power 3 and 10 power 3 get cancels, and therefore it is become 4, remaining is 10 power 2 10 power 4, that is become 10 power 6 into 2. That 2 we multiplied inside. So we are always in an entire FEM in matrix, the higher value what is the things is there, like 10 power 5 or 9 like that will take outside, and the rest of that decimal will going to write inside. Because if you write it inside, multiply the 10 power 6 inside, everywhere you should multiply like 10 power 6 10 power 6 10 power 6. So it makes confusion, and also it problem become it is difficult to solve it when you are going to solve. So therefore, not to avoid that the difficulties, we are taken commonly the 10 power values outside, that is 10 power 6, and only 2 we multiply by inside. That is step number 2. Step number 3. Step number 3 is what is that? Assembly of global stiffness matrix. So here only one element, therefore the K1 is nothing but that is only the global stiffness matrix. Next, step number 4. We need to find global force vector and global displacement vector. That is F. How many forces are there? F1, F2. Therefore, always global force vector as well as displacement vector are column matrix. That is F1, F2. Therefore, F1 what is F1 acting? Here F1 is 0, but F2 is, in a given problem, what is F2 is given, that is nothing but here it is acting 10 kilonewton, convert into Newton, therefore it is 0 and is 10 into 10 power 3. So we will write it in a flower bracket or flower insert synthesis. Similarly, global displacement vector, that is capital Q. So how many nodal displacements are there? That is only 2, Q1 and Q2. That Q1, Q2 we write it in a column matrix type and in a square flower bracket. Therefore, that Q1, Q2 only we need to find. Let us keep like that only. And step number 5, we are going to write the equilibrium equation. So equilibrium equation nothing but KQ is equal to F. The corresponding KQF value we are written now. That is KQF. All three are we written. Now step number 6. It is very important. Keep this now. Now we need to apply the boundary conditions. So using which method? Elimination method. So as I told, in using elimination method, so what are the end conditions are given, corresponding rows and columns are going to be deleted or eliminated. Here at node 1 it is fixed, therefore there is no displacement, therefore corresponding nodal displacement Q1 become 0. Hence eliminate the corresponding rows, that is, and column, that is first row and first column, because in the given problem here it is fixed, here node number 1, that corresponding Q1 is 0, therefore that is the end condition now given. Therefore corresponding first row and first column, first row is first row, this one, and first column we are going to delete, strike it off. Now what is the remaining things? 10 power 6, it is only 2, 10 power 6 into 2 and corresponding into Q2 is equal to 10 into 10 power 3. Now we can solve Q2. Therefore the displacement at node 2 become 0.005 mm. Similarly, step number 7. So we got nodal displacement. The second question is we need to find stress, strain as well as reaction. That is the third question. So first we need to find the stress, means we need to find strain. So we know strain is strain displacement into Q, that is B into Q. We know B is 1 by L minus 1 and Q is nothing but displacement vector, that is Q1 and Q2. We know Q1 is 0 and Q2 we already find out it. And you multiply, matrix multiplication you have to do. How to do the matrix multiplication? This is one of the basics. So first row into first column, like first row into, suppose if it is 2 plus 2 matrix is the first row first column, first row second column, first row third, and so on, like that. Here this into this, therefore what you will get? Minus 1 into 0, 0, 1 into 0.04, that is 0.005 only. And now if you simplify, you will get 5 into 10 power minus 6. This is the strain. Therefore once you got the strain, now we can find the stress. The stress is nothing but, according to the Young's law, E into epsilon. Therefore E is already given, epsilon is we find out it. Therefore stress is 1 Newton per mm square. It is plus, that means that tensile force is acting. So now last step, that is step number 8. We need to find the reaction. For that, R is equal to KQ minus F. We already know K is global stiffness matrix. We know this is a global displacement vector, that is Q1, Q2, and this is global force vector F1, F2. Corresponding values we are substitute. K value is this one. Q1 means 0, Q2 means 0.005, F1 is 0, F2 is this much. Now you simplify. So how to simplify? See these two in a multiplication, then we need to subtract here. First row, first column, first row, first column, second row, first column. So therefore, and finally we need to subtract this, including 10 power 6 is there. Keep this in mind. Now after solving this simplification, you can directly do it by calci. So in a scientific calci, we have a matrix option. You can correspondingly enter these values and directly you can get this. I don't have calci here, otherwise I could show it. You can check it in any videos. Okay. Now therefore once you solve through calci, then R1 will get minus 10 power into 10 raised to 3. It is unit is Newton. This is my unit is Newton, and R2 is 0. So we can validate that. So where is the reaction is produced? Always where is the fixed point? Here only the at node 1 it is fixed. how much you are applying, thus much is the reaction according to Newton, right? Minus, it is 10 kilonewton, it is nothing but minus 10 kilonewton will be the reaction. And at node 2 there is no reaction because it's not fixed, therefore it is, here R2 is 0. So this complete the problem. So the problem is totally 8 marks will be there. So now what are the steps is there, it is same for all the problem. So this complete the first problem on the first case, that is uniform bar with the axial force.